So yesterday, 2 days ago, I asked you to get an assignment done about K and KB problems and stuff like that. And it was pretty well done. We're still having a little bit of trouble making the association with, if I have a base, what does a base make when it's added to water? OH, and because we're saying that bases, okay, they make hydroxide, and what's the equilibrium constant called for a base reacting with water? A Kb. And from the hydroxide, we're going to get a POH. Do you know what I mean? It's the base version of everything, right? So when you add a base to water, you have to be able to identify that you're adding a base to water, and you have to know that, well, your X is going to be the hydroxide concentration. You have to turn your Ka of the conjugate acid into the Kb, and you are going to make a pH, or probably going to make a pH. You have an assignment that I said was due today, but we're not done this stuff, right? So it's going to be pretty darn hard to make sure that it's done today, so why don't you just hand it in tomorrow? If you finish it today, hand it in today, right? Is that okay? If you finished it today, hand it in today, but yeah, we were going to mark it together, but there's no time because we didn't finish. So let's mosey. Let's kind of go as fast as we possibly can through this. I don't know what page is this. This is page 5, 6. 5. Bottom of page 5. You didn't get this booklet? Yeah, it's in the thing. It's in the blue bin, right? Okay. The faster we finish, the faster you can start working on your assignment, or you can start working on something else. So here we have the titration of ammonia with hydrochloric acid. So what in here is my titrant, and what in here is my analyte, or my sample? What's the sample here? Max, what's ammonia? Ammonia, right? So we're starting at a really high pH, so basic. So in here, I want to be very, 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 very specific. Before you add any of your titrant, before you add any titrant at all, what's basically the only thing you have in here? A base. It's not a strong base. I want to be super clear about that. Ammonia is not a strong base. For every one ammonia that you add to water, do you make one hydroxide? No, you don't. Okay? How do we know that? How do we know that ammonia is a weak base? How do I know? Okay. Max.
Well, if you look at the table, its pH starts at 11, not 14.
Oh, yeah, okay. So if we look at this, if we look at the titration curve, the pH starts at 11, not at 14. Yeah, okay, I would agree with you. If this was a strong base, this pH would be, I think, 13, maybe, I don't know, whatever, it doesn't matter. But it'd be higher than 11, right? So we know that this is a weak acid, or a weak base. Let's take a look at this. What's the only substance I have in my solution before I've added any hydrochloric acid at all? What's the only thing that I have in my solution?
Ammonia.
Ammonia. We only have ammonia. And then, slowly, as I start adding my hydrochloric acid, a reaction occurs. What's the reaction that's occurring between the ammonia and the hydrochloric acid? So, I don't know. What's the strongest base that we have in our solution right now? NH3, right? We have a little tiny bit of hydroxide, but it's like 1 out of 100. It's not a large concentration. So our NH3 is reacting with what? What are we adding to the NH3?
HCl.
HCl, right? Am I going to write down HCl? No. Why did I write down that we're adding hydronium instead of hydrogen chloride? Jordy? Hydrochloric acid doesn't exist in water, right? Hydrochloric acid doesn't exist because it's a strong acid. It immediately 100% turns into hydronium. So really, when you buy a bottle of hydrochloric acid, you're buying a bottle of hydronium and some chloride ions. So those are the worst equilibrium arrows ever, but hopefully you get it. What's the reaction here? What are we going to make? NH4 plus ammonium and water. So let's use this reaction to guide our description of the events as this pH curve, or as this titration occurs. So in the beginning, there was only ammonia, right? And then God added hydronium, and then what happened?
The seventh day.
And then the hydronium reacted. Every single time I add a hydronium, it reacts with ammonia to make what?
Ammonia.
Ammonium, right? So in here, in this section right here, we still have some ammonia. Still have some ammonia. But what else do we have? Now that we've turned some of the ammonia into ammonium, it's almost like we've got this weird mixture of ammonia and ammonium. Are we okay with that?
Yeah.
Yeah. Max?
In describing that area in red, could one say it's perhaps a buffer region?
I don't know, Max. Could we say that it's a
That's the buffer region.
buffer region?
Maybe.
Could we? I don't know. Whatever. Yeah.
You asked Miss Newton.
Yes, we will. We asked Miss Newton. Okay. So let's try this out. Where's the equivalence point? I'm getting it just below 6, but it's around 6, right? That's the equivalence point. So all the way up until here, we've got this mixture of ammonia and ammonium. And at this point right here, what happens, what's unique about the equivalence point, Denver?
The substances are both equal.
So we have equal amounts of this and this. For every one of these, we have one of these, right? What that means is that we've added just enough hydronium to turn all of the ammonia into ammonium. And we had no extra left over. So what's the only substance that I have really available at that point? Do I have any ammonia left over? No, because it all reacted with the hydronium. Do I have any extra hydronium at that point? At that point, what do we define that point to be? Equal or equivalent amounts of that and that, right? So for every one of these that reacted, one of those that reacted, and absolutely no more. So the only thing we have is ammonium. Let's take a look at this curve, and let's see if this sequence of events makes sense. Does it make sense that we only have ammonia, what we started with at the beginning?
Yes.
And then slowly we're turning some of the ammonia into ammonium, and at some point in time, we have just ammonium. But then what do we keep on doing? We're still adding hydronium, right? Is there any ammonia left over to react with the hydronium? No. So now, from here on, we've got this weird mixture of weak acid and hydronium. Sorry, I shouldn't say and. I'm going to put a slash there. So which one of these is going to overpower the other? Which one has a greater influence on the pH? The hydronium has a way bigger influence on the pH. So now this is just overkill. Is anything actually reacting anymore? No, there's no more reaction. It's just that now we're adding so much hydronium that we're drowning out any other compounds that are in here, any other substances that are in there. Are we okay with that? So that's why yesterday we said, where is the end of the reaction here? Is the end of the reaction at 90 seconds? No, the end of the reaction is at 65 seconds or something like that. 60 whatever. Okay? Hopefully this makes sense. We're gonna go through this again. So now we have a titration of CH3COOH. I want you to do the exact same thing we just did. I want you to label the different areas and tell me what things are present in those areas. So at A, at B, at C, and at D. What are all the things that are present in those areas?
It's not a peak, it's a ammonia. No. Ratatouille is in there. Something along those lines.
It is a good.
He calls Remy Ratatouille. That's not his name.
No, that's not.
Exactly.
Ratatouille is a dish.
Exactly.
It's a meal. It's something you eat. You don't eat bread.
Yeah.
Ratatouille.
No. They've got Ratatouille.
See, Mash, it's a play on words. He's a rat, and the meal's called ratatouille.
Frank.
What? What was that? He does look more like.
Boomer, just like
I agree. But he's oh. Yes.
My name is Frank.
Okay. That should have been a fair amount of time. At A, what's the only thing we have really?
Oh.
CH3COOH.
We only have our sample, right? That's the only thing. We're starting with our weak acid. We're starting with our sample, right? So we only really have CH3COOH. Aqueous, aqueous, sure. Okay, at B, what's happening to the what's happening to the acetic acid as we add hydroxide? We're gonna make water, sure. But what else are we gonna make? What the hell's the name of this thing? It's the name of it is not the conjugate base of acetic acid, but it is the conjugate base of the acetic acid. What's the name of the conjugate base of the acetic acid? Not acetone. Acetate. Acetate. Okay, so when we just add a little bit of hydroxide, a little bit of the hydroxide reacts with a little bit of the acetic acid to make a little bit of acetate. So at B, we still have some acetic acid left over, right? We haven't reacted all of it, but now we've got this interesting combination of weak acid. It's always the weak acid and its conjugate base, right? That's always what it is for a titration like this. Okay, at the equivalence point, what do we only have in here? The acetate, right? All of this is reacted with all of this for the most part to get acetate. And then when we keep on titrating, what do we have left? we've got our acetate, and what?
Lots and lots.
And lots of OH. That's why the pH has skyrocketed, right? That's why the pH is getting really darn close to 13. It's because we're adding this 0.1 molar hydroxide. Okay, any questions about that? No. All right. What I want you to do is I want you to figure out which one of these diagrams represents the titration of a polyprotic acid with a strong base. You have 30 seconds. Done. Good. It's pretty easy, right? Yeah, you know. Goes wild.
And if it's an acid, then it's
Polyprotic acid.
Yeah.
So like if it has to
How many? That's okay. So a polyprotic acid can give away more than one hydrogen, right? So this is it giving away first hydrogen, that's hydrogen, right? And because what are we starting with? It's the titration of a polyprotic acid. So what are we doing? Okay, that was 30. That was more than 30 seconds, but whatever. So let's go through these. How do you want to solve this question? Do you want to just look for the appropriate answer, or do you want to go through one by one and see why it can't be it?
Yeah, let's do that.
Let's go through this one by one. But I'm going to underline some information. You stop me when I should underline some really, really super important information. Which of the following diagrams?
All of it.
Which of the following diagrams represents the titration of
Underline.
Yeah, there you go.
with a strong?
Underline.
So what
Strong base.
are we starting with an acid or a base? Starting with an acid. So what can you immediately rule out from here? Which letters?
B.
So B, how can you rule out B? Its pH is above 7, right? Starting out. That means we're starting with a base. That's not good, and that's not good for the same reason. What does polyprotic mean? That's basically what this is asking, right? What does polyprotic mean?
Give away more than one hydrogen.
You can either give away if you're an acid, or you can accept if you're a base. You can give away more than one hydrogen in separate chemical reactions. So we've got giving away one hydrogen here and giving away another hydrogen here, right? Those are the two separate chemical reactions. Good. How hard is that question? If you saw that on the diploma, would you be happy or sad?
I cry very.
Okay, now we're on to buffer regions. Buffer regions are whenever you have a mixture of a conjugate acid and its conjugate base, but it has to be a weak acid and a weak base, okay? So a buffer is whenever you have similar concentrations of weak acid and its conjugate base. Hey, where have we seen that before? Combinations of a weak acid and its conjugate base. What section is it?
You tell me.
You tell me. This is our buffer region, right? Where we have approximately equal concentrations of weak acid and its conjugate base. Hey, what do you know? This is a little bit misleading because we're doing a really fast titration here. But what's the slope of section B compared to the slope of section C? Is it a larger slope or is it a smaller slope? It's a smaller slope. It's a less slanty slope. Okay? So what that means is that our pH is changing much less in this region than it is in this region. And that's often the case, that's always the case for buffers. So this is a buffer region.
It's like when the YouTube video you're trying to watch is loading, and like all of a sudden it just starts working.
Oh yeah, the circle's going, and then boom, all of a sudden it loads, right?
Exactly.
Okay, that's a buffer region. Is this a buffer region? I don't know, the slope's not very slanty. Why?
It's the weak base and the conjugate acid doesn't exist down there.
It's so what's in here? If we are we starting off with a base or an acid? Starting off with a base. So down here, all we have is its conjugate acid and hydronium, right? So down here, there is no mixture of conjugate. Oh man, that's the worst J in the world. That's okay. Acid and conjugate base. So that's not a buffer region. That's just we've added so much hydronium that the pH can't change anymore because we just added so much hydronium. That's what the pH is going to be for the rest of the time.
Steve's just there.
Steve's just there. Okay, what's a characteristic of a buffer region? What's important about a buffer region? Why is this region kind of special compared to this part of the buffer or this part of the titration? Is the pH changing dramatically in here? No, not really. It's not changing dramatically, and that's a good thing. We utilize buffers all the time. For example, your blood. I don't know if you talk about this in Biology 30 because I'm not a bio person, but in Bio 30 or Bio 20, do you talk about how your blood has a buffer in it? The buffer is hydrogen carbonate. And so when you eat an orange or when you drink orange juice, is there a lot of acid in orange juice? Yeah, there's a lot of acid in orange juice. The amount of acid that's in orange juice would kill you if you did not have a buffer. If your blood did not have a buffer inside of it, that would kill you because the pH change would be so dramatic.
Is it possible to drink?
Is it possible? Yes, it's possible. There's also lots of sugar in orange juice, and so if you drank too much orange juice, first of all, it's really hypertonic. There's lots of dissolved stuff in orange juice, so it would pull the water out of your organs and into your blood, and so you would be in a state of high blood pressure, and you would be dehydrated because you've been drinking too high concentrations. So there's solid lemon juice. What if you just chug? I don't know. I don't know about lemon juice, Jordy. I have no idea what the I don't know. It's up there. It's really high.
A way to go out.
Okay, let's try this. Here we've got two different situations. I'm going to add hydrochloric acid without a buffer, and then I'm going to add hydrochloric acid with a buffer. Okay? Now, this is hydrogen chloride gas, but whatever, it doesn't really matter. As soon as the hydrogen chloride touches the water, what does it turn this water molecule into? Hydronium. As soon as the hydrogen chloride touches this water molecule, what does it turn it into? Hydronium. Has that been a really, really big change in our pH?
Yeah. Sort of.
Well, we started with 2, 4, 6, 7. We started with 7 water molecules, and 2 of them, so approximately 29% of our solution is turned into hydronium. That's a huge change. Okay? Now let's add hydrogen chloride. Let's add hydrogen chloride to a buffer. What makes a buffer? 2 things. What makes a buffer? It's a conjugate acid, a weak conjugate acid, and its conjugate base. Do you see a weak acid and its conjugate base in here?
Yeah.
I see HF and F minus. So we've got a little bit of acid, we've got a little bit of acid, and we've got a little bit of base, but I don't see a ton of hydronium and I don't see a ton of hydroxide. As soon as the hydrochloric acid gets added to this thing, what's it going to react with? It's sure as hell not going to react with the water. Alicia? It's going to react with whatever the strongest base is in here, right? What's the strongest base in here, Alicia? the conjugate base, right? Yeah. So the HCl, it's going to react with the F to turn it into HF. When I added the HCl, did my pH change? Did I make a ton of hydronium? No, that's weird. I added the same, okay, let's do it again. Let's add HCl. What's it going to react with? The F at the bottom. And we're going to get HF. That's weird. I've added the same amount of hydrogen chloride, but has the pH changed the same amount? Not even close. So a buffer, it has the ability to sacrifice either an acid or a base to maintain the current pH levels. That's the purpose of a buffer. If you add an acid, it's going to react with the conjugate base. If you add a base, it's going to react with whatever the conjugate acid was. But either way, you're sacrificing the conjugate acid or the conjugate base so that the pH doesn't dramatically change. It's the same thing in your blood. When you add a bunch of acid into your blood after you drink orange juice or something like that, that hydrogen carbonate, the carbonic acid hydrogen carbonate buffer that you have in your blood, the hydrogen carbonate immediately reacts with the hydronium, and so your pH doesn't change that much. Let's think about this in a different way. Let's write this reaction that we just saw. F minus reacts with, we'll call it hydronium now. F minus reacts with hydronium, and when it reacts with hydronium, what are we going to get? H2O and HF. So let's use Le Chatelier's principle. Let's add some hydronium here. When I add hydronium to this reaction, what happens? So the concentration of hydronium spikes up, and where do we shift? To the right. We shift to use it up. If I added 5 hydroniums, we're going to shift so that we're going to use up 4 of those 5 hydroniums. So we're going to mitigate the pH change. That's the purpose of this. So we shift to the left to use up the hydronium that we added. So the conjugate, the weak conjugate base reacts with the extra hydronium to minimize pH changes. And with that, unless anybody has any real questions, I mean, we're pretty much done. There's a couple more things on here, okay, and we're going to go through them. But for the most part, that's all the information that we need in order to do the entire equilibrium unit. At some point in time, do you think I can keep adding HCl's forever and I would still be able to buffer this thing? No. What happened already? I ran out of the conjugate base, right? So now, at the moment I add HCl, now my pH is going to start changing really dramatically, right? And so that's what we call buffering capacity. It just, all that means is that at some point in time, we can buffer it, but at some point in time, I'm going to run out of my conjugate base, and then all of a sudden the pH is going to change really dramatically. That's all buffering capacity is. You don't really need to know much about buffering capacity. Just that at some point in time, you're going to run out of that conjugate base, and that's the end of your buffering capacity. Okay, so what substance could we add to a solution of nitrous acid to make a good buffer mixture? What substance could we add? Could we add hydrogen fluoride? What does nitrous acid look like? What's the formula for it? HNO2 aqueous. So if I had a mixture of this, is that a good buffer mixture or buffer solution?
I don't know.
I don't know. What did we define a buffer solution to be?
Oh, it's the conjugate base.
What, Shelby, why is it not good?
Because it can give away more, like it can like give away one hydrogen.
Okay, so but remember, a buffer has to be able to, a buffer has to be able to protect against both acids and bases, right? Can this thing protect against bases? Can it sacrifice itself and react with a base?
Yeah.
Yes. That means the other thing has to be able to sacrifice itself and react against an acid, right? Alicia. Would it not just be the conjugate base of this? So let's add something that has, well, what the hell's the conjugate base of nitrous acid? Nitrite, right? NO2 minus. Well, what kind of substances might have nitrite in them? Rattle off some for me. Would lithium nitrite have nitrite in it? Yes. Would sodium nitrite have nitrite in it? Would potassium nitrite have nitrite in it? So anything nitrite. So we could say potassium nitrite or sodium nitrite or whatever, rubidium nitrite, doesn't matter. Okay, now do the other one. What substance could we add to a solution of sodium carbonate to make a good buffer solution or buffer mixture? Max, you got this?
Hydrochloric acid.
Oh my
Am I wrong again? Well, because like you can sacrifice the hydrogen to make it.
Or you could just use the conjugate.
okay, and here's the thing. The problem, Max, the problem is when I sacrifice HF, I'm gonna make F minus.
Yeah.
That's a bad F or whatever. And these two things have totally radically different KBs. They've got totally different KBs. So one of these is going to be good at buffering at one pH, and one of these is going to be good at buffering at another pH. So why don't we take the really simple approach
Hydrogen carbonate.
of adding something that has hydrogen carbonate in it, right? So what has hydrogen carbonate in it?
Sodium hydrogen carbonate.
Sodium hydrogen carbonate. Potassium hydrogen carbonate, lithium hydrogen carbonate, rubidium hydrogen. Are we okay with that? Yeah. Diploma question. Answer the diploma question. And then I'll let you do your stuff. Matthew, you bugging.
I think it was
He's bullying you.
yeah.
Oh, that's such a good. I didn't even thank you so much for throwing them under the bus. I appreciate that. Shelby and Logan, you have to take your.
And?
Oh, and Mark, I didn't even see it.
See, I wasn't. It was Matthew.
Yeah, I know.
Point your
Mark
finger
has
at
it.
someone else.
I know, and I love his Pokemans too. But
What's a
I'm trying to sound like a boomer. Can you leave? Because I said that?
Yeah.
Hey, try this. Diploma question. No, shut up for a second.
Like a boom.
Ready to do it? Good. I'm going to give you 30 seconds to answer. Then we're going to move on. Oh! Sometimes the printer screws up. And there might be like just an extra sheet of paper. Oh, yeah. Yeah. So that it didn't actually properly attach that page. Sorry. Okay, enough people are just talking and visiting right now that I'm assuming we've all answered the 2 questions. Aiden, can I bug you, buddy? Yes. Okay, Aiden, I'm gonna bug you. Okay, the answer C. Can we move on? Yes. No, we can't. I don't know if the answer is C. Let's work it out. No, calm down. The graph of the student's titration above. Let's look at the titration above. So, are we dealing with a strong acid or a weak acid? Okay, we're dealing with a weak acid, and I want to ask you why. Why? How do you know we're dealing with the titration of a weak acid? Yeah, it starts as at something K, but I want to let you know weak acids almost always have a real kind of little bit of a sharp rise, and then we get the buffer region. If this was a strong acid, if we started with a strong acid, this is a Chem 20 thing, but we would have gone straight into the rise like that. There would have been no kind of bump up on a strong acid, okay? But, anyways, with a strong base on the graph, buffering occurs at what? Region 2 or region 2 and 4? 2. 2 only, right? Region 4, we just have excess base. Good. Awesome. Good job, Aiden. Okay, next question. A buffer solution could be made by mixing equal concentrations of citric acid and what?
It's conjugate base.
It's conjugate base. Which one's the conjugate base of citric acid?
It's A and B.
Wait, no, I'm wrong. C. It can't be A and B. It cannot be A and B. Why? Because you said so. Okay. This is citric acid, right? What's the conjugate base of citric acid? It's the one with 2 COOHs and 1 COO minus, right? Good, okay. So it can't be A or B, and what's the purpose when a small amount of a strong acid is, and what? It's buffering a pH change, right? It's trying to mitigate a pH change. Okay, and the very last one, which of the following chemical pairs can act as a buffer? Can A act as a buffer? No, that's a strong acid, strong base. Can B? 2 strong acids? No. C? No, that's a weak acid and a strong acid. D? By default, yes.
It's like the most obvious one.
Yeah. So, you have time to work on your buffer. You have time to work on your assignment that's now due tomorrow. You have time to work on your review booklet. You have time to work on, what's the other thing I gave you? The big package of diploma questions, right? I'll see the question. Okay, fire away. No. I'm going to turn this off now.